Hello, I will be explaining how to do motion in one dimension. So chapter 1 of the physics book is titled Motion in One Dimension. What does this mean? Well, motion in one dimension means that if you have motion like you're traveling, that means you can only go in one direction, basically. So think throwing a ball up vertically. If I can throw it up somewhat vertically, throwing this up vertically, that would be motion in one dimension, assuming that it doesn't wobble, which it does. But that would be motion in one dimension, and throwing it would be motion in two dimensions. But just throwing it up would be motion. If I just did this, that would be one dimension, one dimension. Okay, you got it. So we have two things to discuss. We have vector quantities. Actually, more than a few things. Vector, and then we have scalar. So what is a vector quantity? Well, if you remember back to mathematics, a vector is basically like this arrow kind of shape thing. Draw it. A vector is this arrow shaped thing. And that's kind of what a vector is here, and it will be in later chapters. But right here, it's just trying to show directional information, right? And the best way I could show this would be displacement versus distance. So displacement, which would be the change in an object's position, is a vector quantity. The scalar equivalent would be distance. So you have, I would draw this out, get your vector, scalar, distance, displacement. Okay, so now that you understand that, or I hope you do, I can kind of show you an example of this, right? So let's say that you are going from your house. You go 2 miles to... Alright, so from the house you go 2 miles from the store. You got your stuff from the store, then you go back 2 miles to your house. What is your distance? Well, any kindergartner could know that. It's just 2 plus 2. That equals 4 miles. So your distance, written as d, equals 4 miles. And your displacement, written as delta x, that is triangle x right there, your displacement will be, well, what do you think the displacement will be? Will it be 4? Will it be 6? What will it be, right? So the change in the object's position, you start at your house and you end it at your house. What's your change? Well, for this hypothetical, it would basically be 0. So 0 miles would be your displacement. So your displacement is not equal to your distance. I'm trying to think when it can be. It might be able to in some scenarios. I've never seen it. I feel like there's a way that it could be, but I haven't actually seen that. But if you can figure that out, then you should do that. Try to make an example where the displacement would be equal to the distance. Oh yeah, I mean you could do one. You could use the same problem. Kind of dumb here. You could just use the same problem. You could use the same problem, and if you never went back to your house, your displacement would be the same as your distance. Yeah, but very rarely is it like that. Typically, you do return back to your origin of starting point, or your origin. So, okay, so I'm just gonna read it on your own, the problem 1.1 on page 8. An ant starts at his anthill and walks 15.2 centimeters to a crust of bread. He takes the bread, turns around, and walks back towards his anthill. He stops after he's traveled 3.8 centimeters and eats a part of the crust of the bread. What is the total distance? I hate problems like this because they're stupidly descriptive. So basically, the ant don't know how to draw an ant. He goes 15.2 centimeters. And then he goes back 3.8 centimeters. So his displacement would just be 15.2 minus 3.8, which would be 11.4 centimeters, and then his distance would just be plus 3.8, which would be 19 centimeters. So it's pretty simple. It should take you like, I don't know, 10 minutes to get the grasp of this concept. It's pretty simple. Just basically you have to look at it, is this character, or whatever's moving, close to the origin point? And if so, how far away is it from the origin point? That is the displacement. I should write that down. That's actually a pretty good definition. So when you're solving for displacement, the question I want you to ask yourself is how far away is it from the origin? And the origin is the place that it started from. And then the distance is just how much, distance, how much ground, you keep using synonyms, but how much has it traveled, basically. How much total has it traveled? So these are two questions I want you to ask yourself. When you're doing displacement, how far away is it from the origin? When you're doing distance, how far away, or how total has it traveled, right? It went 2 miles there, 2 miles back, 2 miles there, 2 miles back, 5 miles there. What's the total distance, right? For displacement, how far away am I from the origin? You just do how far away am I from the origin? That's distance and displacement. So next, let's move on to, I have a cool little fun experiment. So this is a cup of water, right? It's at this line. So the displacement of this water, if this would be the origin, this line would be the origin. When I drop in this kind bar, that's the only thing I could find, it goes up pretty roughly, it goes up a good amount, but that would basically be the displacement, right? The displacement of this water. Okay, so let's move on to speed and velocity. They're very different, they're very similar, but they are quite different, right? So you may think, oh, they're the same thing, my velocity is the same as my speed. I think it can be, but it's not always. Because it's based off, I'll just show you the formulas. Gotta stop erasing my finger. Okay, so speed is delta d over delta t, and then velocity is delta x, or displacement, over time, delta time. That's the change in time. Whoops. Okay, so speed is defined as the time rate change of an object, while velocity is defined as the time rate change of an object's position. Those sound very similar, but they're not. And the reason they are is because if you go back to displacement, what we just talked about merely 10 seconds ago, velocity is based on displacement, right? So let's go back to that store situation, right? You went 2 miles to the store, 2 miles, you went 2 miles to the store and you went 1 mile back, because your displacement has to be, sorry. We go 2 miles to the store and we go 2 miles back. Your displacement is 0. Meaning your velocity is 0, but your distance, let's say it took me 180 seconds somehow, that's really quick. But yeah, let's just say it takes 60 seconds to go 2 miles there, 2 miles back. I don't know how. So what we have to do So 4 miles total. The distance is 4. So you have a distance of 4, and then over, wait, I don't think I'm doing this right. Let's say you did 400 meters, because it's much easier in meters. 400 meters over 180. It's pretty slow. Your speed is 2.22. The reason you can't use miles, you can, there's just a conversion factor, and I'm blanking on the conversion factor right now. So yeah, see if you did 400, yeah, so you should do 400, so I'll show you. Here's how the speed and velocity are different, and they're different because they're based off of displacement, or they're based off, one's up, okay. Velocity is based off displacement, and then speed is based off distance. So that's the difference between those two. They're very similar, and later I think I might get time in this lesson, but velocity is relative. I should get into that. Unless that's chapter 2. It might be chapter 2. So we can do, I don't really want to do an example. We can. So you pedal example 1.2 on page, I don't want to just go through the book, I think it's boring. Okay, so we covered speed and velocity. They're not too hard, they're pretty easy, and remember, they're based off of displacement and distance, which are very different. You can rewind to find where to find them. So just to find them. So, okay, so let's go through. Alright, let's do 1.3, because it seems like to be a pretty simple 1.3. A boat travels straight down a river at the speed of 15 meters per second. If the boat travels a distance of 34 kilometers, the boat travels a distance of 34 kilometers, how long was the boat ride? So what formula should we use for this? So the formula would be, are we trying to find velocity? Yeah, we're trying to find velocity. So, wait, no, we're trying to find time. We have the velocity. Yeah, so this would be the formula. Very simple formula compared to the other ones that we'll get to. So 15 is this velocity. So velocity equals 15 meters per second. Always write down your givens. That's the first thing I would always do. The displacement is 34.1 kilometers, and the time is your unknown. So we can go and do 15 equals 34.1 over t. Set it up like this. Okay. So now all we have to do is multiply by t on both sides. Just use some algebra. So you have 15t equals 34.1. 15. So you get t equals 2.273, and that would be in hours. I'm gonna look that up. I'm 90% sure I'm correct, but on the off chance that I'm incorrect, that would be really embarrassing. So this is 1.3. That's not in hours. Whoops. Okay, I got tripped up. That is 200. Wait a minute. Whoops. I didn't turn this up. Okay, so one thing that's really tricky about this, trips me up too, you have to pay attention to the units. So I was given the velocity in meters per second. What I didn't do is I didn't convert my 34 kilometers to the distance. Now this is a pretty easy fix. Just 34.1 times 100, and I don't think it'll focus, bro. Yeah, so you get 3,410, and then you divide that by 15, and you get 200, basically 230 seconds. Divide by 60, you get, no, it's 2,300 seconds. Divide by 60, you get 38 minutes. So it's times 1,000, sorry, not times 100. This is probably the most annoying part of this chapter, is just remembering to keep your units, because I can't even do that, and I've been studying physics this entire summer. So I would always remind a note to you, keep units keep the units consistent. That is probably the best advice I can give you for this chapter. This chapter is very simple, but a simple calculation mistake like that, like, distance is given in kilometers, but the speed is given in meters. Well, I need to fix that, right? And if you don't fix it, you'll get the wrong answer and it will not be fun. Okay, so next on to average and instantaneous velocity. So this is also pretty, actually I don't remember this so much, but, so this is on page 13 for those following along. Give me some goals. So the average velocity is the velocity of an object over an extended period of time. Makes sense. I say long period of time, I'm writing it down. But it really just means an extended period, which could be how long, could be however long the problem requires. Okay. So they're kind of different, but they're kind of similar. The book does a fun little experiment. We'll probably do that in class eventually. I'm not gonna do that with you. I can do these fun graphs though that I actually really hate, but they're really important and they're not too hard to read, I don't think. Look at figure 1.3 on page 16. So this is pretty simple, just rise over run for slope. Rise over run. So I'm gonna try to find, yeah. Let's just do on your own. Yeah, I mean, experience is the best teacher. Just try on your own. 1.4. Okay, so is an object moving? Okay, so if you look at the graph, 3.5 seconds. It's like halfway, and it's like moving. At like. No, I'm gonna teach this. 3.5. It's like moving at 8, so 3.5 is like moving at like 8 meters per second. That's the position. And then at 8.5 seconds, it's moving, I would say like 3. So the object is clearly moving faster at 3 meters per second. That's the answer. How many times does the object change directions? It's quite an interesting question, because I don't think it does. I think it's a trick question. Oh no, it changes directions once, because it goes into the negatives. So if you look at probably around 11.3 seconds, it changes and goes negative. 11.3 is basically the neutralizer, when it's at 0, I forgot what it's called. So it changes directions once, because it goes positive and then it goes negative a little bit, so that would be a change of directions. So it changes directions once. What is the instantaneous velocity at 1 second? The velocity at 1 second is probably like 1. It's in the middle of 0 and 2, so I would assume 1. Yeah. Okay, so now we're going to what I referenced before, which is that velocity is actually relative. This is pretty fun. So velocity, just like time, is relative. Okay, so velocity is, this part of velocity is kind of confusing, but when you think of it as displacement, you'll get the hang of it. Example 1.5 is pretty good at explaining this. So a car and a truck are approaching each other on a 2-lane road. One car is going 56 miles per hour, while the truck is going 45 miles per hour. So the velocity would just be, the truck driver would see 101 miles per hour. And the reason is, I could do this running would probably be an easier example. Say these people are running towards each other, not going to hit each other, but they're running towards each other. One's going 10 meters per second, it's wildly quick, but he is. And then the other one's going 5 meters per second. I don't know, maybe he has like steroids. I don't know why he's going so fast. So 10 meters per second and 5 meters per second. So the displacement, right, if you add these two, right, it's 10 and 15. So are they both experiencing 15? Interesting. So I think the man is experiencing 15 meters per second. I don't know what's the car standing, 15 meters per second. Yeah, but you can see how, if you're going in a car, if you're in a car and a car speeds by you, you really feel it, right? It goes, you really feel that, right? Why? Well, it's because you're already going at high speed and that car is going high speed. So it's because of the wind of that, the forces colliding, because the wind makes your car shake. But I believe, okay, we're going to acceleration in just a second. Let me understand this. Yes, the car observes, so they both experience the same velocity because they're both colliding with each other. So it's kind of relative, I think. But I'm pretty sure it's the same. I'll clarify that in a later video, maybe. But I don't know, just read the book, see what it says. I don't really know what that means. It's a little bit confusing. Now we're going to a much easier topic, which is acceleration. So acceleration is the time rate change of an object's velocity. Think of a car going 0 to 60 in like 2.3 seconds, right? Think of that. So A equals velocity over time, and that's, you have to have delta, because the time can change and the velocity can change, and that's the average velocity then. No, that's initial minus final velocity, sorry. Okay, let's just jump into a problem. Okay. Example 1.6. A car is moving with a velocity of 25 meters per second to the east, and then he slams on the brakes and the car comes to a halt in 2.1 seconds. So, yeah, so you have to do the final versus the initial. So, yeah, you only have the initial, so you don't have the final. And delta V equals final minus initial. So it equals final minus the initial. So what you have to do for these, it's, so you have the initial velocity, right? I think it's called VO, right? So you have VO equals 25 meters per second. Okay, so the delta V is negative 25 meters per second. Why? Well, because the final is 0. The car comes to a complete stop, right? We know that, right? That's why, the car comes to a complete halt in 2.1 seconds. So the velocity of that car would be 0 So the final velocity of the car is 0. The initial velocity is 25 meters per second. So 0 minus 25, negative 25. And then we have the time of 2.1 seconds. So time is 2.1 seconds, so that does not change. So negative 25 over 2.1. Negative 11, probably negative 12, rounds to negative 12. So negative 12 meters per second is the car's acceleration, because it decelerates. In this book, well, in physics, acceleration and deceleration are the same thing, because acceleration is a much more broad term. You can say deceleration, but it is the same thing. It's kind of confusing, but you'll get used to it. And then, yeah, that's what the book says. So, yeah, let me get a little bit of time. The rest of the chapter, I should just finish this chapter. This chapter is not, I don't want to say not too hard if you're struggling with it, but it is the fundamentals, and the fundamentals of physics are a little challenging. This is like the really, really basic fundamentals. This entire book is a fundamental course. So average and instantaneous acceleration. I'll just read the book. Since the equations for velocity and acceleration are similar, you might expect that acceleration, like velocity, can be defined as average or instantaneous. Just like velocity, when the time interval is large, the acceleration is large. When the time interval is infinitely short, however, the acceleration is instantaneous. Just like velocity, the only real way to determine instantaneous velocity is by studying graphs. Fun. I actually hate graphs. Okay, doesn't mean you should though. You should really like the graphs. So over what time interval is the car? So look at example. Actually, just look at on your own 1.11. Okay, so during what time interval is the object's speed increasing? So I can't really draw the graph because it's kind of complicated. But if you look at it, it kind of has this between 6 and 14. This kind of is like peak. So that's where it's increasing. And this, like, the graphs of this are kind of interesting because it's not too hard. You just need to know how to interpret graphs, which is pretty simple. But you don't use you use acceleration much later on, like in chapter 2. So, but for right now, all we have to do is just find, so 6 to 14, that's the time. That is where it is increasing, because it goes here, goes up, and then basically, maybe like 13, maybe cut it off at 13, because that's 14 is when it starts to decelerate. And then asks, when's the object acceleration 0? So you can see, you just read the graph, 16. So I hope this chapter isn't too hard. It's kind of a fundamental course. The graphs are a little bit tricky. They get trickier in chapter 2, and then they disappear. So once you get past chapter 2, there's no more graphs, and I'm very happy. So let's recap. There's a few parts of this chapter. So the first part of this chapter is, I'll just like draw in a graph, like vectors, vector and scalar. Right, that's like part 1 of this chapter, right? Vectors and scalars with, displacement, distance, your speed, your velocity, all that fun stuff. And then you also have speed and velocity. So that's the second part. So these are defined by the formulas v equals displacement over time, and then speed equals distance over time. And if you're making a note card, you should make a note card. I'd highly recommend you put those on there. And then you have, your average and instant velocity, instantaneous velocity, which is just reading graphs. But it also has some like slope, rise, overrun stuff. I didn't cover that, but you can look at the book. And then, your velocity is relative. So that's basically, if you are moving at 0, car comes whizzing by, what's the velocity for the car? That's basically what it'd be. Then you have your acceleration. And then you have average and instantaneous acceleration, which is actually much simpler than the velocity in terms of the graphs. It's much easier to read. So I hope this was helpful. This was meant to be a full introductory course, or video, whatever it is, on chapter 1 of this book. I don't know who's watching this, of this book. So it's pretty simple. Try some on your own problems. There's some more problems at the back of the book that you can try. And if you need help, I should be free to help you. Okay, thank you for watching.